here, asking you about DPO and RLHF. Okay, great. Why don't you turn to somebody and compare your answers? Okay, so there's still pretty good, there's a lot of disagreement on one of these. For the first one, it's false. Does somebody want to tell me which one does not learn an explicit representation of the reward function? So they do not both learn one. One of them does and one of them doesn't. Which one does? Yeah.
Because RLHF learns and then DPO doesn't learn.
That's right. Yeah, that's exactly right. So this one does learn. Okay, so this is false. Now it's true that DPO assumes a particular parametric representation for the reward model, both of them do, but DPO then inverts that so you can directly do policy learning. It never has to explicitly learn a reward function in the same way that RLHF does. What about the second one? What do you think? Is it constrained to be as good as the best examples in the pairwise preference data? So I think this is false. Does somebody who also said false want to say why? This is false. Yeah. Yeah.
Maybe because we're using like a policy approximate, using a function to approximate it, so it could be, so the gradient could like take a step which is like more positive than.
Yeah, exactly. So what I said. So you're going to, at least if we think about the RLHF case, we are using this information to learn a reward model. If that reward model is good, even and can sort of extrapolate beyond and generalize beyond the samples that we have, when you do PPO using that reward model, you can learn a policy that's better than your demonstrations. So this can, in fact, go beyond the best sort of performance that's inside your data, or if you think of it in terms of the reward, maybe some of the examples you're showing aren't that great, but then you can use that to actually get a better policy. And in fact, you might think that's probably exactly what's happening with ChatGPT, because for ChatGPT, they initially got sort of the fine-tuned model from supervised learning, and then they showed those examples to people, and people would pick between them, and then it learned a reward model, and then they got a policy that was better at generating those sort of responses. So you could argue that ChatGPT is an example that suggests, yes, this often can be true. We can learn a good enough reward model such that if we do PPO, at least a little bit of it, we can actually outperform the training examples. PPO, DPO does use a reference policy, both of them do. And this idea will come up, we've seen it a few times already, and it'll continue to come up today. This idea of thinking is essentially of how far can we extrapolate or how far can we interpolate from our data, and when do we need to sort of constrain ourselves to be fairly close, either in the policy space or something else, so that we don't generalize to parts of the domain where we might have really bad performance. We saw that in imitation learning, we saw that in DPO, we've seen that in PPO, in all of these cases where we're thinking, given the data that we have, how can we sort of generalize as much as possible, but not further. All right. Okay, so we're getting into a part of the class, which is probably my favorite part of the class, though I like, of course I'm biased, I like all of it, but we've been talking about sort of learning from past human preferences. We first saw that sort of learning from past human demonstrations, then we saw learning from past human preferences. And today we're going to think just generally about learning from past data. So that could be generated by humans, or it could be generated by your robot or something else. And then next time we're going to start talking about fast or data efficient learning. And that's going to be useful for doing homework 3 as well, because the theory question for homework 3 is focused on data efficient learning. All right, so we'll focus on that now. So in particular for today, we're going to discuss, like we often do, sort of thinking of separating things into a policy evaluation question and then a policy learning question. Because we've seen repeatedly that if we think about, can we evaluate how good a particular policy is, that we can often combine that as a way to sort of bootstrap improving our policy optimization. All right, but I want to start with just a question, which is, can we do better than imitation learning? And of course, this relates to the question I just asked you in the refresh your understanding. So I'm just going to give up sort of an example. In my lab, we often think about education data or healthcare data or other cases where decisions are being generated by humans or automated systems, where you might have, say, a series of patients. You could think of this as medical record data. And each of those people are getting a series of interventions. Maybe it's some medication, maybe it's a medical checkup, maybe it's a vaccine, and then we observe some sort of outcome. And in imitation learning, we saw the idea of saying, well, could we try to mimic the best human, or could we try to mimic expert data? And so an important question is whether or not we can go beyond that. And we just thought about one example where we might be able to go beyond that. But I think that there's a huge number of places we'd love to be able to go beyond the limits of sort of at least the average human performance. Healthcare is certainly one of them. In America, we pay a lot for our healthcare, and we don't have particularly good outcomes compared to how much we are paying. So you would hope that maybe we could learn through sort of reinforcement learning or others, are there better sequences of decisions we could make in order to better assist, say, a new patient? Okay. So I'll just give a little bit of backstory of why I started thinking about this question. So maybe about a decade ago, I was collaborating with Zoran Popovic in his lab and my grad students. He's at University of Washington, and he had this game called Refraction. And refraction helps teach kids about fractions. It's one of the concepts kids typically find really challenging when they start to learn math. And so in it, you have a spaceship, and you're trying to fuel a spaceship by splitting laser beams in certain ways, so that you create fractions or subparts of laser beams to fuel spaceships and to sort of save the agents. And in this case, so I think roughly around maybe 500,000 kids have played this game. And what we were thinking about is how could we customize it to make it more personalized and adaptive to students. So in particular, there were all these different sort of game activities and game levels, and we wanted to understand how could we use a sort of information about how the student was working in one of the activities to adaptively select which next activity to do. So this is a decision policy, and you can imagine conditioning on all sorts of state features. So state features could be like how long they took, but it also could be things like where did they put down laser beams, or what series of mistakes did they make. You imagine it could be generally a really, really rich context or state space. And then there were lots of different next levels we could do. Okay, so that was the question we were interested in. And in particular, in this case, we had access to about 11,000 learners who had been giving activities in a random order. Now that was because there was a human designer who had designed a specific sequence through the game, but we weren't sure if that was actually optimal or close to optimal. And what we wanted to do is to see whether or not we could find, using reinforcement learning, an adaptive policy to help students persist at the game for longer. So this game was offered on something called BrainPop, which some of you guys might have seen before. It offers lots of educational games for kids. And a lot of kids use it for a little while and then they stop. So it's an optional game. And we had some evidence that suggested that if kids played the game, they were likely to learn things. But if they don't play the game, they are not. So we wanted to think about increasing student persistence in terms of like the number of levels. And so we really wanted to go beyond expert performance in this case, like beyond what the experts had done. And so what we did is we used reinforcement learning, and we wanted to see if we could outperform essentially behavior cloning. And to give a spoiler of sort of the types of ideas we're going to see today, in this case we found we could learn a policy that increased persistence by about 30%. And so that suggests that in some of these domains, there may be essentially be enough data and evidence to find new decision policies that are substantially better than what is being currently done. And so that's what inspires me in my lab a lot, is to think about where can we use natural variation in the decisions that are being made, or past experiments that were run, in order to find substantially better decision policies than are currently being used. Yeah.
Not a super relevant question to the subject matter, but just out of curiosity, was the 30% distributed uniformly, or was it just like the people who already played longer, or the ones that stopped early would actually continue?
This is a great question. So this is a really big challenge often, is whether or not, who are you moving inside of this distribution? So this is just an expectation, like most of what we've been doing for Q-learning and others. We did not analyze that too much in this case. In another much more recent paper we have, which I think came out in January or something, we did exactly that analysis to try to see who was actually impacted. And there we're really excited that it was the lowest performers that were most impacted. And that was exciting because one of the big concerns is that a lot of these systems are just increasing the inequity gap. And this is particularly a problem in kind of these optional ones, because it's normally the kids that are furthest ahead that have the highest usage. So great question. But it also sort of raises, in terms of on the technical side, these questions around understanding sort of predicting estimates for subparts of the population and doing heterogeneous treatment effect analysis to figure out which groupings of contexts have different forms of Q values. Yeah?
Can I ask, in terms of the policy, what was sort of being changed at like the simplest level? Is it like the difficulty of the fractions? Is it how hard it goes as they're growing up, or?
Yeah, it's a great question. So in this case, I can't remember what the final exact policy was they're using, but the type of things that were varied in this case is things around the fractions, so like changing the numbers, as well as different things of sort of how tricky it is graphically to do that. So there was a couple different things that we could manipulate, as well as you can see just like visually here, these look quite different. So one thing that we found in some other work in a game called Battleship Numberline, which I was excited because recently my son uses BrainPop and it just popped up and I was like, we worked on that. So that was exciting. In Battleship Numberline, which is another thing to do with fractions, we found there that variability was incredibly important for persistence. And so just changing sort of how things look, in that case, how big the battleships were, also makes a very big difference to persistence and engagement. I think that's actually an interesting question too, in terms of including the history and the state features to try to capture stuff like people caring about variability. So great questions. We'll talk a little bit more about this example later to talk about some things that we tried or that didn't work in this domain. But this is just to highlight that I guess we shouldn't set our expectations too low. So I think that imitation learning is amazing. And of course, if you're trying to imitate the best surgeons in the world, that's incredible. But there are many cases where we think we can go beyond human performance, particularly in cases where kind of like our high-level principles don't inform what we should do at a more micro level. So for example, here we might have general principles of learning science, but it doesn't say, which activity to exactly do when. And that's where being data-driven can be really helpful. Okay, let me give you another example. Another thing that we think about a lot is healthcare. We've collaborated a lot with Finale Joshi-Velez at Harvard and her lab. This is an example thinking about hypotension and trying to optimize different policies for that. There's a really amazing data set called MIMIC that comes out of, I think, MIT and MGH, Mass General Hospital, which has lots and lots of electronic medical record systems. And so what these guys did in this particular paper is to look at behavior policy, so that's this flat line, and to see if they could learn policies using a method called popcorn that they thought would be much better. And again, here, the results depend on the method and some of the hyperparameters they're looking at. But the important thing just to notice here is that a number of these policies are substantially better than baseline, suggesting again that there may be domains where we can leverage the intrinsic variability in the data and identify things that are working much more successfully in this systematic way. So when we think about doing this, generally I would call this sort of offline or batch or counterfactual RL. And it's counterfactual because what we're trying to do is to estimate or learn policies that don't exist in the actual data collection strategy. So we have the setting now where we'll assume, like in imitation learning, that we have a data set of end trajectories. So we're going to assume now we're going back to the standard MDP setting, and it's not pairwise preferences. We're just back to having sequences of states and actions and rewards. Okay, so. All right. So in particular, we may have things like this, where we have data from one policy and data from another policy, and we want to think about how we can learn from that, thinking about the state distribution of what's actually best. Okay. Now I'll just highlight here 2 reasons why this is hard. So we're always trying to estimate a counterfactual here over what might have happened that wasn't tried. So in this case, we don't know for this patient group what would have happened if we gave them that treatment or vice versa. So just a reminder, this is the fundamental problem of sort of causal inference, and this is going to be a big challenge for us here, particularly when we try to go beyond the performance of the policy we saw in the past. Okay, so data is censored, and of course, in general, again, we're going to need generalization because we don't want to have to enumerate all the possible policies. Okay. And I do just want to highlight here that in addition to education and healthcare, if you want to think about climate change or many other areas, there's just a huge number of scenarios, including robotics, because it's often really expensive to do robotics experiments, where these types of ideas are helpful. Okay. Now, one thing you might be wondering about is when I'm talking about this, and I'm talking about trying to understand the performance of a new decision policy that was not used to gather the data, you might start to think back to Q-learning. There's a lot of work on off-policy reinforcement learning from really, the very beginning of reinforcement learning. So you might say, why don't we already have the tools that we need to try to tackle this problem of learning better policies? And in fact, as we saw, ChatGPT, if we learn a reward function and we do PPO, that is doing off-policy learning. So that's one example. So why can't we do this? Why can't we just do Q-learning or some of the other methods we've seen? One thing to remember is a little while ago, I said sometimes we have this deadly triad of bootstrapping, function approximation, and off-policy learning. That sometimes when we combine all 3 of these things, things can fail. And that was part of the motivation for PPO, is that we don't want to go too far from the distribution. Let me just talk a little bit about what can happen here in the context of Q-learning, sort of model-free learning. So this is the BCQ, Behavior Constrained Q-Learning from Scott Fujimoto. And what this shows here is that, so these are a bunch of different methods. This is DQN, Deep Q-Learning. This is behavior cloning. This is the behavioral policy. So what they did is they gathered some data, and then they tried to use different methods to learn a policy from it. And this is DDPG. And what they found with this is that some of the methods did really bad, even given the behavior data. DQN does about the same as the behavior data. But what they found here is that by being a bit more careful and using methods that were explicitly designed to handle this offline data, in this case BCQ, Behavior Constrained Q-Learning, they could do substantially better. And so that suggests that we don't probably just want to use, if we know our data is fixed and we know we're not going to get additional data, that it may be worth it for us to use different types of algorithms in order to handle the fact that our data is constrained and we're not going to be continuing to get fresh data. Okay, so that sort of motivates why we're going to need new methods. All right, so now what we're going to do is dive into policy evaluation, and then we'll talk about policy optimization afterwards. So in batch policy evaluation, what we're going to be thinking about is we have a particular policy of interest, and we have a data set, and we'd like to be able to use that data set to estimate how good that policy is for one state or on average over a set of starting states. Okay, so similar to what we've seen for policy evaluation before. Okay. One thing I want to highlight, this is by Phil Thomas, who I had the privilege of having as my postdoc a few years ago. He is a professor at UMass Amherst. We generally want to think about sample-efficient methods for doing this. So in this case, he was working with Adobe, and they have 10 million to 20 million trajectories. Doesn't matter too much what these lines are. The key thing here is that this is sort of the behavior policy, and you want to be learning policies which you're confident are better than your behavior policy. And this is just to highlight that depending on the methods you use, you may be confident at very different points. So just meaning that data efficiency and having good algorithms is going to matter a lot. Yeah?
By behavior, you mean the policy that was observed in the current data set?
Exactly. Behavior policy, great clarification, Christian. When I say behavior policy today, what I mean is the policy that was used to gather the data set that you have. So I'll just write that out on here. So we're going to assume behavior policy is the one that was used to gather your data. Okay. All right, let's first think about using models. So this is actually the first thing we tried to do with refraction. We thought, okay, great, Travis Mandel, who is the grad student leading the project, we have all this historical data. Let's just try to learn models from it. So we're going to look at, we're going to represent the state space in some way. And then under different actions, here in this case, that's just different levels, and there's only a finite number of levels and activities. Let's learn a dynamics model. So in this case, the idea is that we have that existing data set, and we're going to learn an explicit dynamics model, and we can learn an explicit reward model. Now, in our case, our reward model was known because it's persistence. So we could essentially get a reward every time the student didn't quit the game. But we didn't know the dynamics model, and so that's what we're using the data to learn. Now, as you might imagine, we had to make a lot of choices here about what state representations we would use. And so we thought about lots and lots and lots of different state representations. Okay, but once you have that, then you can treat this as a simulator. So now you have your simulator of the world because you have a dynamics model and a reward model. Either you can do this analytically, like in some of the methods we saw in some of the first few classes, or you can use dynamic programming or Q-learning, Q-evaluation with those to explicitly learn what the value is. But really you can use anything. You can even use like Monte Carlo methods because you can try to learn from this simulator an optimal policy. So you can either try to learn an optimal policy or you can evaluate a specific one. You can do either of those, so I'll just write that here. So you can either evaluation or learn a new policy with EQN, any other RL method. Because now you have a simulator. Okay, let me show you what happens. All right, so the first thing I'm going to show you is the following. What we have on the x-axis here is different state representations of this environment. So these are obviously really small state spaces, like we don't actually think that human learning is encapsulated in terms of 5 states or 10 states, but you can just imagine sweeping this, right? Like, so these are some of the state spaces we consider where we'd use really, really condensed state spaces or much more complicated ones. What this is showing here is normalized score, and this is log likelihood. And this is held out. So what this is saying is, as you might expect, as you increase your sort of state space complexity, you get a better fit on the data. You can better predict the next state of the student if you use a more complex state space. And that's not totally surprising, right? Because we think that human learning is complicated, and so we really think we are getting a better dynamics model. And again, just to emphasize here, this is cross-validation, so this is on a held out set. This is not training error. Okay, so we're doing better in terms of this. Now, what are we doing with these once we have these? Oh yeah, go ahead.
The number of samples are fixed.
Yes, yeah. So the data set size is fixed here. What we're trying to do is, given the data that you've seen before, like there are all different ways. We just have clickstream data. There's tons of ways to model that as state spaces, and we're just doing model selection. Now, what we were doing here then is once we had that simulator, we were trying to learn a good policy. And then we were evaluating the performance of that actual policy. Now, I'll tell you how we actually evaluated that policy shortly, but this is the important thing. So This is saying that the models that we're getting are actually better, okay? But here's the problem. If I take this policy, which really, or if I take this model, which really is a better model, it really does fit the data better, and then I do, say, dynamic programming with it, and I extract an optimal pi star. So that's the procedure. I take my model, I learn an optimal policy, and now I want to know how good that actually is in the real world. If I evaluate that in the real world, even though the model itself was actually better, what you can see is the actual value of that policy is getting worse. Okay, so I've got a better simulator, but the policy I get by optimizing for that better simulator is worse. Okay. So this is the actual unbiased reward estimator, and I'll tell you shortly how we do that. Because of course, under the model's opinion, the model thinks it's, the policy it's helping produce is great. Let me just make sure that sort of the pipeline of what we're doing there is clear. So what we do is we're going from data to a model of the dynamics model. And then we add in a reward function and we extract a pi star for that estimated dynamics model. But that's just under the simulator. And then what I want to know actually is what the true value is of that policy I've computed. Okay? And what this graph is showing is that even though under my model is getting better, the actual performance of the value I'm getting out is getting worse. Now, when we first saw this, we were kind of confused. We weren't quite sure why this was happening. And in fact, there had been some work a few years prior to this in sort of the educational data mining community that suggested doing exactly what we were doing here, which was build a model, then use it to simulate and learn a good policy, and then deploy the policy that looked best. Okay? But what our work here suggested is that it was not a good idea. Now, the reason for that is because the model is misspecified. Now, that means that under this model misspecification, the value it's getting when it computes the optimal policy, so you can think of there being two things here. There is one thing, which is v hat of pi hat star, which is its own estimate of how good its value is. And then there is the true value of it. And these in general are going to be different. And these in particular are going to be different if your estimated model is bad. So it's going to think, I'm doing great. This is going to, help students persist till the rest of time. But if the model is misspecified, meaning that even with infinite data, it will not converge to the true model of student learning, then that estimate will be wrong. And as you might imagine here, 20-state model of human learning is not that great. Yeah, question.
You are improving 10-state, right?
Yeah. So it's not saying that some of these policies might not be good policies. What this was arguing to us, so it's a great question. It's not that inside of these there might not be pretty decent policy classes. You could argue that education works because there's decent-ish policies. I mean, I don't have perfect models of all of you guys' learning, but it's still sufficient for us to be able to learn and communicate. What I'm arguing here is that we should not just use the accuracy of the dynamics model as like a proxy for which of the values or which of the policies to pick. There's arguing that we need separate independent estimates of we want to basically, in some ways, kind of like what we saw with PPO and policy learning, we would like to directly evaluate the performance of a policy instead of using as a proxy sort of how much our Q function is changing or how accurate we think our dynamics model is. Yeah.
So when we evaluate the policy, we execute it under the real environment or estimate the policy performance using our estimate model?
So there's two things. We can do it under our simulated model or we can do it under our real model. We don't want to have to do it under our real model because we want to know which policy to deploy before we actually deploy it. Otherwise, we could kind of be doing online RL. So what I'll shortly be giving you is a way to get an accurate estimate of how good the policy is before we deploy it. I haven't said how to do that yet. I've just argued that using models alone might not be good. Do you have a
Yeah, so about model misspecification, is one way to think about this just like you're kind of overfitting your dynamics model kind of increasing the number of states that you used to represent it, or?
But we're not, here's the question going, we're not overfitting here because it really is a better fit. It's still just not a perfect fit. Another way I might say this is it's not realizable. This is not the real model of student learning, and under this that means that there's still essentially significant bias when we do this learning. Now, one thing I just want to note is like model-based learning can still be helpful. One thing that we may want to do in this case is explicitly build different models when we know we want to evaluate different policies. So normally when we fit a model, we try to minimize the loss under the data distribution of the behavior policy. So like if you have a bunch of data and you fit your dynamics model, you're essentially trying to optimize for the accuracy over your behavior policy. But if you know that the policy you want to evaluate is different, you can actually change, essentially you can weigh your errors separately. So this is a paper that we did a few years ago with Finale Dashi and Yao Liu and Omar Gottsman and others, which just highlighted this, that you could change your loss function and essentially upweigh your accuracy over the state and action pairs that you think you will encounter under a different policy. And that can help a lot. So what you can see here is, this was for a medical domain, and what you can see is that this green here is ground truth, and what we found in this case, so ours was our model here, and this is just if you fit for the behavior policy. And what you can see is by essentially reweighing your data, you can fit dynamics models that much better fit the type of dynamics you'd see in the future. Okay, but now I'm going to introduce sort of model-free methods, and then we're going to get into important sampling as other ways to try to do this policy evaluation that hopefully have different limitations or less limitations compared to the model-based method. So one of the first methods that I'll talk about here is fitted Q evaluation. So fitted Q evaluation is going to look pretty similar to deep Q learning, but there's just going to be a couple important differences. So our data set here is a bunch of just different tuples of state, action, reward, next state. Recall that our Q function, Q pi, is just going to be the immediate reward we got for being in that SI tuple, so whatever we saw in our data set. And then we'll put in plus gamma times v pi of si plus 1. And then what we do is we try to minimize the difference between this under a parameterized function, just like what we saw with deep Q learning, versus the observed data tuples. So you can think of this as our target. Okay. And this is called fitted Q evaluation. It's closely related to something called FQI, which is fitted Q iteration, which I think was around 2015, 2005-ish. And so this is very similar to what we've seen with deep Q learning before. We just fit this function. The key thing here is that we want it to be for just a single policy pi. So we're not doing an argmax. So this is how the algorithm works for fitted Q evaluation. We sort of initialize our Q function randomly. It could be a deep Q, a deep Q network. It could be something else. We compute the targets where when we put in the next Q, we have to use the policy we're interested in evaluating. So we're only doing this for the actions we would take under the policy we care about. We build our training set of sort of X's, actions, and our output Q target, and then we fit our Q function. And so again, the key difference here compared to DQN is there's no max. We are fixing this part. Only for a fixed pi. But aside from that, it should look really similar. Okay. And so this was something that was very closely related to a common algorithm for doing off-policy learning, which is fitted Q iteration, which is very related to deep Q learning. And one of the things people wanted to understand is whether this thing that was working in practice actually had some theoretical grounding behind it. Like, could we say anything formal about how good this approach was? So just to give you an illustration of the types of guarantees that we can get in this case, what we want to look at in this situation is to think about sort of what is the generalization error. Okay. Now let me put this in here. Okay. So I won't go through the whole paper. I just want to give you an illustration of the types of guarantees that you might get in this setting. What they would like to know in this case is to compare the difference between the value that you will compute under this procedure versus the true value of the policy. This is your normal discount factor, and then there's a whole bunch of things that are additional. Let me highlight some important things here. N here is the number of samples you need. So N tells you about how much data you're going to need in order to do this. So this is sort of how much data. Okay. Epsilon is sort of your desired target accuracy. Okay. This is one of the really important things. So we're going to have something called a concentratability coefficient. Concentratability coefficient is going to be the difference essentially between the distribution of state action pairs that you have in your data set and the distribution of state action pairs you would get under your desired policy. So we saw this before with PPO, of thinking about sort of these divergence in the state action distributions. State action distributions. Okay. And it's also related to what we'll call overlap later. So I won't go through all the details in this case, but I want to just give an illustration that people often think about trying to understand if you have a data set of some behavior data, how accurate you can hope to be of evaluating the performance of a policy depends on your discount factor, because that says sort of how accurate you want to be and how much you care about long-term rewards, how much data you have in terms of your target error, and how closely related your state action distributions are from your training set to your test set or your desired policy. Now, one of the challenges about this approach is that it generally still relies on the Markov assumption. So we're still assuming our data is all Markov, and it relies on our models, in these cases, the sort of Q functions, being well specified. So what do I mean by that? It means that we really can fit the Q function. Like there's some existing Q function in the world for our policy and we can really fit it. And if you say, for example, let's say that this is your state space, it's just one-dimensional. And this is what like your true function looks like. You know, you can imagine that it looks something like this. And let's say that you are restricting yourself to fit a line like that with just two parameters. So in that case, even if you had infinite amounts of data, you're still going to have a lot of error. You're not going to be able to fit the Q function. So these methods assume typically realizability, meaning that if you had infinite data, you could fit the function. The problem is that you don't have infinite data. Okay. All right, so now we're going to see a really beautiful method called importance sampling, which allows us to deal with this. We've seen sort of brief ideas about this before, but I'm curious if anybody who's seen this in other classes. Who's seen importance sampling before? Okay, so just a couple people. This is one of the favorite ideas in CS234, according to some past people. All right, so the idea, what is the motivation? So importance sampling is an idea from statistics that we have imported over into reinforcement learning. Why would we like to do this? Well, we want a method that doesn't rely on the models being correct, meaning that we can actually, that fit things with a two-layer, deep neural network or stuff, and that we don't have to rely on the Markov assumption in the state space we're using. We saw before that we could use Monte Carlo methods to accomplish this for online policy evaluation. And now we want to do this for offline data, meaning that we have data from a different distribution from the policy we want to evaluate. And the key challenge, as has often been, is data distribution mismatch. Okay, so here's how importance sampling works. Let me just specify what this means. Let's say we want to try to understand the expected reward over a distribution of states. So for this part, you can just think of x is equal to states. And R of x is equal to the reward of a state. This works for very, very general distributions, but you could think of that here as just being rewards. All right, what we're going to do is the following. This is what we would like to evaluate. So you could think of this here as maybe being P of x could be equal to the probability of reaching x under policy. So So you might really want this. You might want to know what is the expected reward I'm going to get under this policy, where I know what my reward is for each state, or I have samples of it, and then I have this probability distribution. The problem is that you don't have data from that. So but no data from P of X. So that's the general challenge we're in. We want to see how well like our alternative policy would work for like helping students persist, but we have no data from that. So here's the trick. Let's multiply and divide by the same thing. I'm going to introduce a new policy and its distribution Q. Okay, so Q of X is a different policy. It's just a different policy. Maybe it's going to end up in different states with different probabilities. Okay. So let's rewrite this. This is going to be equal to Q of X times P of X over R over Q of X, R of X. Okay. All right, I haven't changed anything yet. This is exactly equal. But if I have data from Q of X, I can approximate this expectation with samples. So this is approximately equal to 1 over n, sum over I equals 1 to n of x sampled according to Q of X, P of xi, Q of xi, R of xi. This is super beautiful. What we've said here is that I really want to estimate the expectation of something over, say, this policy P. I don't have any samples from P. What I can do is I can just take samples from my policy Q and I can reweigh them. So it says if I was, really likely to reach a particular X under policy Q, but less likely under this one, I'll weigh that data less. If I'm much more likely to get to a state xi than I was under here, I'm going to upweight those samples. So this is beautiful and it's unbiased. So this is an unbiased estimate. And we'll extend it in a second to think about multi-time steps. But just for single time step right now, this is how we can do this. It gives us an unbiased estimate, and as we'll see shortly, we can extend this to multi-time steps and we don't have to make a Markov assumption. Okay, so this is a really lovely idea. So we can compute this expected value under an alternative distribution, and it is generally an unbiased estimator under a couple of assumptions. The first is that the sampling distribution Q, so like our alternative policy, has to be greater than or equal to 0 for all x such that P of x would be greater than 0. What does that mean in practice? That means that if you could reach a state under your policy you care about with a non-zero probability, so let's say, I don't know, your student could get to this particular level with non-zero probability under your target policy, then there has to be some probability you'd also get there under your training data set. This is sort of reasonable, right? So this says that like, if I want to think about, I don't know, a policy that like recommends restaurants versus coffee shops, I can't use that data to then estimate how good it would be to go to the movies. I just have never done that. There has to be, for anything that we're trying to estimate here, we have to have non-zero probability for that x. The second thing is a little bit more subtle, but comes up a lot in real empirical data, which is called no hidden confounding. And that means that essentially you have to know all of the features that were used to kind of define this distribution. So this may not seem as clear in this part, but I think once we start getting into multi-time steps and the sequences, it becomes really relevant. So let me give an example. Okay, so imagine like a healthcare setting. So if we go back to that electronic medical record setting, we often are interested in what would have happened to a patient if we did a different action. So we want to know what that counterfactual is. One of the challenges there is that we will have certain features that are in our electronic medical record system. We will see an action, like, someone was taken to surgery or some drug was administered, and then we see the outcome. In order for importance sampling to work, all of the features that were used to make that decision or pick that action have to be known. And that's called no hidden confounding. Now, why is that? Well, it might be, for example, you might see that there are certain patients that are sick, and then a particular action is taken, and maybe they die. And you might see other patients that look like they have the same features, and a different action is taken, and they live. And in that case, you might think, oh, maybe the decision was just bad. That's possible, but it's also possible that there are just hidden additional features that you don't have in your data, and that meant that the first person was much more sick, and that's why they got that particular treatment versus the other person. So it might be that, that there's important reasons that are not part of X that are being used to define what the action is in the data set. And in those sorts of confounding scenarios, then if you try to use importance sampling, you will not get an unbiased estimator. This is really important and really hard in practice. It comes up all the time. And in fact, one of the things we were just doing on a paper we just put online, we were trying to think really, really carefully about whether or not there would be additional confounding beyond the features that we had in our data set. So in that case, we had done an experiment to see whether or not offering students access to GPT-4 would increase or decrease participation in the class and exam scores. And only some people used GPT-4. A lot of people that were given access to it did not use it. And so an important question there then is, well, is there something intrinsically different about those students who are using it that also would confound their test scores? And so this issue of no hidden confounding comes up a lot, particularly when sort of actions are optional or being made by humans. Okay. Now, if you're in sort of MuJoCo or something, this is easy because if you have control over the simulator, you don't have to worry about it. But it's important to know in practice. All right, let's take a second and sort of check your understanding. So we haven't really talked about bandits yet. Don't worry about exactly this. We're going to be doing policy evaluation. So let's say we have a data set for, I'll just say samples, for samples from 3 actions, okay? Action 1 is a Bernoulli variable where with probability 0.02, you get a really high reward, else 0. The second one, you get probability, with probability 0.55, you get reward of 2, else 0. And the third one, with probability 0.5, get a reward of 1, else 0. Your data is going to be sampled from a particular behavior policy. So this is our what we've been calling a behavior policy, where with probability 0.8, it pulls this action, else it pulls action 2. The policy we want to evaluate, pi2, pulls action 2, else it pulls action 1. This question asks you to think about what are true about the performance of those policies, whether or not we could use the data from pi1 to get an unbiased estimator of pi2, and whether or not the rewards being positive or negative might impact that. The third one is kind of hard and might require looking back at the equations on the previous slides. Water for a second and then. All right, why don't you turn to a neighbor and see what you got? It takes a couple layers for this because we've got stochastic policies and stochastic
I'm pretty sure you can do
What do we think of the second one?
I actually swapped the wish for P1 and those components.
What actions?
Yeah, the second one, I don't see that my
But also it's just like
and third one.
that's 20% efficiency. So it's like 0% chance. No.
I know that requires a couple layers.
Yeah.
No, never said it.
Oh, 3. I did it in my head. So if you go, what is my 2? Yeah, so pull by 2, 0.5, we have 2 there, so that's 1 plus whatever we can pull from action 1, which would be 2, which should give us around 3. It's like, yeah, so around 3. But then the previous one gives us 0.8 at a time to get.
Let's say.
Yeah, you'll get 1, and then so that gives us 0.8, and then otherwise you get 2, which will give us.
Actually, one is a huge negative.
Yeah, so it wasn't as high in my small calculations. And then, yeah.
What about for a second?
So I got my head around this one, to be honest.
Okay, well, what actions do you take in Pi 1? Regardless of the top rate, what actions is Pi 1? Action 1.
Yeah.
You used it for one. You only see action two.
Yeah, which you get, and then what actions do you take?
But you never see action one, which is the thing that the type
But it's action 1.
I initially said yes, and I second I thought this is low.
This action here is like an action, you know,
you never see
action.
Yes. Okay, so they have to be completely overlapping.
Honestly, most of these check your understanding by specific by emotional side.
Because they're like, you never try.
Okay, good, good scheme.
Yeah, so behavior policies.
Okay.
All right, let's go through this. So the first one requires a couple nested expectations. So let's go through those and make sure I get my math right. Okay, so for the first one, Pi 1, so there's 2 levels of stochasticity here. We have a stochastic policy and we have rewards with stochastic actions. So let's first, or stochastic rewards. So let's first just figure out what the expected reward is for action 1. This is equal to 0.02 with reward 100, so that is 2, plus else you get a reward of 0. So the expected reward for action A1 is 2. I'll just write that as here. Expected reward for action A1. We can do the same calculation here. So the expected reward for A2 is just going to be equal to 0.55 times 2, which is just equal to 1.1. And the expected reward for A3 is just equal to 0.5. Okay, so generally, policies that put more weight on action 1 are going to be better. Now let's look at what the expected value is of Pi 1. So what Pi 1 is is it's going to say with probability 0.8, we're going to get the reward of A3 plus 0.2, we get the reward of A2. The reward of A3 is 0.5, so it's 0.8 times 0.5 plus 0.2 times 1.1. Okay. So that's about how much that one is. So this is like approximately, yeah, okay, so we'll this one is like approximately like 0.42-ish. I'll double check the exact math. It's roughly like that. Okay, now let's do it for, so this is the reward for pi 1. We'll do the same thing for pi 2. This says with 0.5, it gets the reward, the expected reward for R of A2, plus 0.5, it gets the reward of A1. So that's equal to 0.5 times 1.1 plus 0.5 times 2. So it's approximately equal to 1.5-ish. I think I was off by 2 when I was chatting to some people before. Yeah.
I got 0.62 for the first one, 0.65 for the second one.
So I do my math wrong. I think it's going to be more than that because the expected reward for this one is 2. And so this one has to be
2. Okay, I thought it's 0.2.
Yeah. Yeah. So I think this ends up being roughly 1.5. I can double check my math, but I think that's right. Okay. So pi 2 does have true higher reward, so this is true. The second is we can't use pi 1 to get an unbiased estimate of pi 2. Why is that? So this is true also. Why can't we use pi 1, data from pi 1?
Because it never does action 1.
That's right. So it never does action 1. So it's like saying you have data about all these restaurants, and then you ask it, okay, I also have a policy that's now going to go to this new restaurant, and you have no data from that. So we can't get an unbiased estimate of the average reward. Okay, this one's hard. This is false. Okay. It turns out that you can still get an unbiased, you can still get a lower bound on the performance of a policy using another policy which doesn't have complete overlap if the rewards are strictly positive. So if the rewards are always greater than or equal to 0, you can do this. Why is this? So we have a paper on this from a few years ago now. Just for why this happens, essentially you can think of it as if your behavior policy doesn't include some of the actions that you want to evaluate, it's like putting 0 mass on those. Okay, because if you think back to what is happening here, it's like you never sample them, right? So you have 0 probability mass on some things that you want to evaluate. Like you want to include a policy that sometimes recommends movies and you never do, so it's like putting 0 mass on that. If all your reward is positive, that's essentially just lowering your estimated value. Okay? So it turns out that if all your rewards are positive, you can use a behavior policy that doesn't have complete coverage with your target policy, but it'll be a lower bound. The reason why that might be useful is because if it's still the case that your target new evaluation policy is better than your behavior policy, even though it might not have full coverage, you may still want to use it. So it's like, oh, it doesn't matter whether those recommendations it makes for like those new movies is good or not, it's already a better policy. So we can do that. Okay, great. All right, so it turns out that we can also do this for RL policy evaluation. So I just showed you a much more simple setting of this, and I'll highlight too here that importance sampling, like many things in stats and math, etc., goes by many different names. You'll often see things like inverse propensity weighting. So if you take econ classes, people often refer to these things more as like IPWs or inverse propensity weighting. When I learned about them as importance sampling. Often also depends whether you're using these to design ways to gather data or whether you have historical data. Okay, let's see how we can do this for reinforcement learning. So in reinforcement learning, we can do exactly the same thing. So I have what I want to have. These are now my trajectories. And as we've seen before, we can think of the value of a policy as just being an expectation over all the trajectories that could be generated by that policy from initial start state times the reward of those trajectories. So this is the reward of a trajectory tau. This is the probability of a trajectory under the desired policy. So what we can do in this case is the following. We can just multiply and divide by the same thing like what we saw before. So we're going to imagine that we have data from a different policy. So I'm going to call this pi b. So I've now introduced my behavior policy. Okay. So I'm just going to rewrite that. So I again just have this weight. This is just reweighing what's the probability of me getting a particular trajectory under my behavior policy versus my target policy. Okay. So we have that here. And let me write it out here first. Okay, so now we know, let me put this from here. We know from before that if we have samples from our behavior policy, we can approximate this expectation by a sampled expectation and we reweight these. The next thing is to make sure that we can compute what's the probability of a trajectory under our target policy versus our evaluation policy. And we've seen things like this before. So just remember what we can do in this case is that the probability of a trajectory given a policy in action is equal to the product over equals 1 to the length of the trajectory, the probability, the transition probability. I'm just going to write it as a deterministic policy for simplicity, deterministic for simplicity, but you can extend all of this times the probability that you would take that action S. Oops. Actually, yeah, I'll rewrite that. I don't want it to be deterministic. That will be misleading. Okay, so let's put it here. Okay. All right. So this is just the probability of us taking the action given the state under our policy and the transition probability for every single time step. The nice thing that we can see in this case, we can write that out for both the behavior policy and the target policy. And as we've seen in some other cases, this will cancel. So you don't need to know the dynamics model. So this is beautiful and incredibly helpful under similar conditions to what we just saw, as long as you have coverage, which means that you will visit the same sort of trajectories, maybe with differing probabilities. All you have to do is reweight them so they look more like the policy that you want to evaluate. And we assume that you know this because this is just your policy probability. It just says what action would you take in this state. And so this is known if you're doing policy evaluation. Okay. So it was first introduced for RL to my knowledge by Doina Prekup, Richard Sutton, and Satinder Singh in 2000. And then there's been a lot of follow-up work and leveraging of this. It's super helpful. We don't need the Markov assumption or anything. Okay. It requires very minimal assumptions. It's unbiased, and it corrects for distribution mismatch. So extremely helpful. I won't do this now, but you might want to look through this later just to think about, given everything you know about Monte Carlo methods, et cetera, like what might be some of the limitations of doing this. I'll just briefly say there's been a whole bunch of extensions. One thing is called per decision importance sampling. Similar to a policy gradient, we think about the fact that in terms of the reward and the decisions, later decisions that are made can't affect earlier rewards. So you can reduce the variance by being a little bit more strategic in where you put your weights. And we saw similar ideas to this in policy gradient. So this is called the per decision importance sampling, and it helps to have better properties in terms of, particularly for long sequences. In general, the variance is pretty high, like for most Monte Carlo methods. one thing to know is there's concentration inequalities, like the Hofting inequality, that you can use that will generally scale with the largest range of the variable if you want to start to get confidence intervals over these values. And this can start to be pretty terrible for long horizons for importance sampling. So I'll post afterwards what the solutions are for both of these, check your understandings, but it's pretty informative to think about exactly how bad this can become. Okay, to deal with this, there's a lot of different extensions. One thing is that you can, if you do have Markov structure, you can think about state distributions instead of trajectories, and that can be very helpful. And there's been a bunch of work in that direction. One work that we've done and others is called is taking ideas from statistics on doubly robust estimation and using these to reduce the variance in these methods, as well as trying to blend between methods that make a Markov assumption and methods that don't. Okay. All right. I want to finish now by talking a bit about how we can use these ideas and others to think about offline policy learning. So I think there's sort of a couple important ideas we went through so far today. One is that you can just build a simulator from historical data, and you can use that to learn, but it may be biased, and that bias may be substantial when you're trying to use it to pick policies. We can do model-free methods, but we're going to want to be careful about those, and we're going to see more of that later. And you can use importance sampling to get an unbiased estimate, but it might be high variance. We're not going to think about those sorts of ideas in the context of when we're actually trying to pick a policy and do optimization. So I'm going to go back to this issue of coverage because I think it's important to emphasize. So let's imagine that you have antibiotics, mechanical ventilator, and a vasopressor, all things that are often used in sort of an intensive care unit. And you might have different probabilities of these interventions. And let's say you want to evaluate a policy that frequently does mechanical ventilation. As we've been talking about, your data has to support the policy you want to evaluate. So if this is your behavior policy, that works because every single action you want to try, you have a non-zero probability of trying that in the data. If you have this policy, that doesn't work. That's the same as the example that we saw before. So if you never use a vasopressor in your behavior data, you cannot evaluate how good that would be in the future. Now, when I draw it like this, or in the example that I gave in the check your understanding, it's pretty obvious because there's a finite number of actions, and it's pretty clear, like if we didn't take action, the vasopressor action, that we can't evaluate it. But in real data sets, it often gets really hard to understand what does it mean to have sort of sufficient coverage. So in general, this is going to be hard because we're going to want to say, well, is it okay? If it's 0, I definitely can't do it. But if it was like right here, is that sufficient? If like 1 in a million times I use a vasopressor, is that going to be okay? Does it have to be in my actual data set, or does it just have to be there was a chance of me doing this? So all these issues over kind of exactly how much data support you need come up. All right. So up to around 2020, most of the methods for doing off-policy evaluation, kind of model-based or model-free, assumed overlap. So if you're doing off-policy estimation, it means for your policy of interest. But for off-policy optimization, it often assumed all policies. So every single policy you can imagine in your domain had to have coverage with your behavior policy. Now, if your behavior policy is random, that's fine. But if your behavior policy is, say, like how physicians operate or how teachers operate or some sort of, policy that's not completely random, that wouldn't always be satisfied. And in general, many real data sets don't involve complete random exploration. And this means if you assume this and use these methods and it's not true, then you might end up sort of going into parts of the domain or ending up taking policies that go into parts of the domain where you have very little coverage. So I'm going to introduce an idea, and it turns out this idea, there was a number of groups that all started thinking about this at the same time, and I'll cite a few others of them in a minute. We called this doing the best with what you got. So the idea was, how can we leverage data sets where we only have partial coverage? Like we still want to do as well as we can, but within the support of the data. And this is similar to kind of the KL constraint or PPO clipping that we've seen before, but this is all going to be entirely in the offline case where we don't manage to get any additional data. And the key idea that we're going to think about here is just being pessimistic. So that when we don't think we have sufficient coverage or we have high uncertainty over what the reward might be in a particular state or action, we want to be pessimistic with respect to that uncertainty. I want to highlight that just even when our paper came out here, there was sort of increasing interest in offline RL. But what we noted is that like there was still quite a few challenges. And I just want to illustrate that with a really simple example. So this is known as the chain MDP, and we might talk about it more when we talk about data efficient exploration. This is not exactly the same as all the chain MDPs, but there's a number of them, and they're used to illustrate the hardness of sort of learning good policies. So the idea in this setting is you have an initial start state S1, and then, S0, and then under one policy, mu, you have a probability of going to S1, S2, etc. And then also with another probability, you have a probability of transitioning to S10. It's a really, really small MDP, just a very small number of states. The important thing to note here is that all of these states have deterministic reward except for this one. So in reality, this has an expected reward of 0.8. You always get 0.8 when you get to that state. And this one has an expected reward of 0.5. So it's a worse state. But if you go there, because of stochasticity, some of the time you'll get a 1 there, which means when you have finite data, you might think that state S9 is better than S10. Okay, that will just happen with your data. So what we could show in this case is that a bunch of the other algorithms for doing conservative batch RL, and I won't go through all of them, but happy to talk them offline, had this weird behavior where this is your behavior data set. So as you increase the amount of your behavior data, you would hope in general that you get a better estimate of a new policy, and you get actually better performance. This is the success rate. And we found we had this weird behavior where for a lot of the other algorithms, they would start off and they would learn the optimal policy for this domain, which is to go to S10. But then as you got more data from your behavior data set, they would get misled because sometime you would have seen S9 and it would have given you a 1. And if it saw that, it would say, oh no, I don't want to go to S10, I want to go to S9 instead. So with intermediate amounts of data, these other methods would get confused and learn a bad policy. And it was only as you started to get a lot more data that they would end up getting back and realizing what the best policy was. And so that was somewhat concerning, right? Because you would generally hope that you get some sort of monotonic improvement as you get more and more data from your behavior data set. But here we were seeing that some of the previous methods had this sort of unfortunate behavior. And it turned out it didn't just happen in for these particular examples, but we could show some other types of examples where we got very similar types of performance challenges for other methods. So the key idea is pretty simple, which is just be pessimistic if you haven't seen a state action very much. So we defined a filtration function, which is just a simple threshold that says, let me check for this state and action pair. It's kind of what my density is, how much I've seen it. If it's greater than a threshold, this is going to be 1. Okay? So what this threshold is doing is trying to account for your statistical uncertainty you have if you have finite amounts of data. So if you haven't seen things very much, this is going to become 0. If you've seen things a lot, it's going to be 1. That's all we're doing. And then we can just combine this with Bellman backups. So just sort of for DQN or Bellman operator, we can just apply it so that when we are looking at your reward plus gamma times your expected discounted sum of rewards, we look at the states you might get into. And if those states we don't have very much data for, then this whole thing becomes 0. And so it's like saying, if I transition to a next state for which I don't have much data, I just pretend its reward is 0. And then I back up from there. Which essentially means I don't want to take actions that transition to states for which I don't have enough data. Just pessimistic. And it's going to be a lower bound. If your rewards are all bounded by 0, it's just going to be a lower bound on your potential reward. Okay, so since we assumed that our rewards were all positive and you can always just shift them, this is going to become a pessimistic estimate for all of those tuples. And you can do this for either policy evaluation or for, so you can use this in kind of policy gradient type approaches or for Q-learning type of methods. Okay. And it turns out this helps a lot. So we call this marginalized behavior supported policy optimization. I'll just highlight what was, because one of the key things of this paper was the theory that we showed with it. As I said, a lot of the previous methods sort of had to make assumptions over coverage, that like your data covered any possible policy that you might want to evaluate. And under that, you could ensure that the policy that you learn is close to optimal. Ours does not make that guarantee. It only says, let's think about all policies that we could reasonably evaluate that have sort of enough coverage. We are guaranteed to find the best policy within that class. And we have some, I'll skip through this now due to time, but under some assumptions, then we can also give these kind of finite sample guarantees, similar to what we saw for the fitted Q evaluation. Okay. All right. And I'll just highlight that those do include the function approximation. So these aren't for tabular. Okay, so this is what's pretty cool to see. So in this case, this was Hopper. This is the behavior policy. So this is the behavior policy used to gather the data. What you can see here is if you use DDPG, that actually does worse than the behavior policy. If you use behavior cloning, it was a little bit better, about the same. It used a particular VAE. We then compared to BCQ, which I mentioned briefly before, Scott Fujimoto's work. And you can see that and our approach in green both do substantially better. Again, highlighting that in some of these cases, the data does support you learning a much better policy. And you should try to uncover that by using these methods that sort of explicitly think about your uncertainty. Now, I'll skip this just due to time. There's some interesting sort of theoretical reasons why model-based might be even better. At the same time, there were 3 papers that all came out about NeurIPS. Ours was one of them, the same year, with all basically very related ideas. Ours was a model-free based approach, and work by some of my colleagues, Chelsea Finn and Teng-Yu Ma and others, learned a model-based approach where they penalized model uncertainty during planning. And they had some very nice results in D4L cases. Ours was a bit more theoretical and model-free. Theirs was a little more algorithmic and empirical, and also had some really nice, and was focused on model-based approaches. I'll just highlight that another method that came out similarly around the same time was conservative Q learning, and that has also continued to be very popular since. So that's another way to think about sort of being conservative. We're almost out of time, so I just want to share kind of how do these different approaches compare. Pessimistic approaches in general do better than alternatives. All of these have some form of pessimism. These are model-based. This is the sort of behavior-constrained Q-learning. This is some nice work there from Sergey Levine's group from Berkeley, and CQL, which is also from Berkeley. The different methods tend to do better or worse in different settings. I think that in general, the key thing to understand from this part is that it really can be beneficial to think explicitly about uncertainty and use that to sort of penalize and constrain your function to be in the parts of the domain where you have support. And again, this is pretty similar. This should definitely make you think back to sort of PPO. And sort of having constrained updates. So in many of these different settings, we're really trying to think explicitly about sort of coverage and how far we can use the existing data we have. But particularly here where we don't assume you don't get any additional data, you're just going to deploy a policy at the end. We want to think about exactly how much support we have. All right, I will skip the last part because we're going to be out of time. If you're interested, just want to highlight that you can extend these ideas to think about there being constraints. So we had a science paper a few years ago thinking about what if you want to make sure your performance is improving compared to baselines. And in particular, we used like a diabetes insulin management simulator. It's a really cool simulator. It was improved by the FDA to replace early stage animal trials, and you can learn new ways to do insulin delivery. And what we wanted to illustrate in this case is that by thinking explicitly about your uncertainty over the performance of new decision policies, you could quickly learn a policy that you were confident would be better than the existing policy. So I just highlight that to say that there are lots of cases where you'd like to do this offline policy learning, but do so in a way where you have safety constraints or constraints over the performance. All right, let me just summarize this part. So in terms of things that you should know or be able to do, You should be able to define and apply importance sampling for policy evaluation and understand some of the limitations of these prior works. You should understand why offline RL might be able to outperform imitation learning. You should know sort of this idea of pessimism under uncertainty and be able to have some application areas where you might want to be doing offline RL or offline policy evaluation. So particularly in kind of high-risk settings, that can be important. What we'll be doing next is going to start to talk about how, if we can gather our data, how we should gather our data in order to really efficiently learn policies. I'll see you on Wednesday.